Hey folks, welcome back. Just wanted to do a quick example of the Newton's second law stuff in circular motion. So we're dealing with objects that are undergoing right now circular motion that doesn't necessarily have to be uniform. So it could be changing speed or it could be constant speed. So just watch out for those changes and how they might affect these problems. So something to remember here, even if they have constant speed, these objects are accelerating. To go around in this circular path, they have to be accelerating. Objects that aren't accelerating go in a straight line at constant speed. So if we just take the case of constant constant speed, not constant velocity, then our acceleration is going to be straight toward the center of the circle. We'll call that centripetal acceleration. And my velocity will always be tangent to the circle, so that gets called tangential velocity. Now, it turns out that there's this really fun vector process to figure out the value for acceleration, or there's also a pretty easy relationship to calculate that if we know the radius of the circle this thing's going on. So r is this distance there. Then we can calculate the magnitude for acceleration just as v squared divided by r. So really nice straightforward relationship to work with. After this point, we can solve Newton's second law problems just like we have been doing. So we've got a way to calculate acceleration. Acceleration is equal to net force over mass. We just need to be careful on the net force that now we're not dealing with the x direction or the y direction. We're dealing with the c direction, the centripetal direction. So let's take a look at a problem that we might solve then. These ball on a string problems are all over the place in the circular motion unit. So that's the first one that we'll start with here. Gravity and orbit will be a problem that we do a lot later on. And then the other one is just an object traveling around in a circle, like maybe a car going around in a circle. And so they all have different reasons for going around in a circle, different forces causing that, but there are a few things in common for these things. So in this one, we've got a ball going around in a vertical circle, like I was just doing with the tennis ball. And that's important because now gravity is a force that can point either toward the center of the circle, or if we're at the bottom, away from the center of the circle. So we got to pay attention to gravity here too. We're looking at the ball when it's at the top of the circle. I think it makes sense to get a sketch down. So we got a ball up here. It's got a tension force down here, and I'll just kind of mark out the circle here. And then it's also got a gravitational force going downward here. Now, we've got the mass for the tennis ball, or for the ball here, is 0.2 kilograms. We can find out what that gravitational force is, but we're asked for the tension force on this one. Let's go ahead and calculate gravity. Fg is equal to m times g. So that's going to be equal to then the mass of 0.2 kilograms times the acceleration due to gravity, 9.8 meters per second squared. And so we get a gravitational force of 1.96 newtons. We've also got the radius for this circle. Well, indirectly, it's a 2 meter long string, so the radius of the circle is going to be 2 meters as well, 2 meters from where the person is holding the string here to where the ball is here. That'd be 2 meters. It's a big circle. So we've got the radius, and we've got the speed up at that point is 3 meters per second squared. Radius and speed together are enough to get us acceleration in the centripetal direction. AC is equal to v squared over r, so that's going to be equal to 3 meters per second squared divided by 2 meters. So that'd be 9 meters squared per second squared over 2. So AC is equal to 4.5 meters per second squared. And then we've got acceleration. We've got one of our two forces known to us. We've got the mass known. We can solve using Newton's second law now. So acceleration, this time in the centripetal direction, equals net force in the centripetal direction divided by mass. We've got acceleration toward the center of the circle is 4.5 meters per second squared. And then two forces both in the positive direction being toward the center of the circle. So we've got gravity, positive 1.96 newtons, plus our tension force, Ft, divided by the mass of the ball is 0.2 kilograms. All right, at this point we'll multiply both sides by 0.2 kilograms and get 0.9 newtons over here is equal to positive 1.96 newtons plus Ft. And we'll subtract the 1.96 newtons from both sides on this one and find out that, shoot, I screwed up. Well, I screwed up, but I don't have time to make a new video. So here's the problem that I ran into. The downward acceleration is only 4.5 meters per second squared. Gravity by itself would make it accelerate downward faster than that. So we actually couldn't have it going around in a circle like this at the end of the rope. It would be accelerating too fast downward. So we need to have this velocity be larger is the problem. So I'm just going to switch that. I'm not going to change the rest of the problem. Sorry, the whole video doesn't make sense. I promise to make a good quality one when I have a little more time. But let's make this 4 meters per second. And then that becomes 16 over 2, which is 8. Nope, sorry. That doesn't work either. Got to make it more than 9.8. So about 5 meters per second. Okay, squared is 25, divided by 2 is 12.5 meters per second squared. And that's toward the center of the circle, which is downward. Gravity can't take care of that all by itself. So now we've got a problem that we can actually solve. 12.5 goes in here. And when we multiply both sides by 0.2 kilograms, then we'll get, that'd be 2.5 newtons, and then we subtract the 1.96 newtons from both sides, and we get 0.54 newtons equals Ft. All right, there we go. Again, sorry for the screw up on the example. I'll make a better one when I have the chance. Thanks for watching. Let me know if you have questions on this, and I'll see you guys on Monday.